Okay, in this section, we will look at graphs and transformations of elementary functions. The objectives for this section are to become familiar with elementary functions, transform functions using vertical and horizontal shifts, transform functions using reflections, stretches, and shrinks, and also graph piecewise defined functions. Okay, in the first graph, we'll look at an identity function, which is also a linear function. We have f of x is equal to x. Notice here the graph is shown and the domain and range are given. It says the domain is the set of all real numbers and the range is also the set of all real numbers. If we were to go ahead and write these in, here we have the domain is from negative to positive infinity in interval notation, and the same thing here. Okay, so whenever you see R, the set of all real numbers, it just represents all real numbers, which include numbers from negative to positive infinity. Okay, the next function is going to be a square function, which is also called a quadratic function. Notice the domain is the set of all real numbers, and the range is from 0 to infinity. So here, let's write the domain negative to positive infinity. Okay. We have a cube function. We have m of x equals x cubed. Notice here the domain and range are also both the set of all real numbers. Notice the graph. Okay, next we have the square root function. Notice here it says n of x is equal to the square root of x. We're given the graph here to the left. And it says here that the domain is from 0 to infinity, including 0, and the range is also 0 to infinity, including 0. So let's just look at this first. We'll do the domain in fuchsia. Here, my graph starts, and since the domain is the set of all x values, of all x's, or first coordinates, but in this case, we're thinking of it in terms of x. Here we have the point 0, 0, and then notice here, this is going to be the starting point, but since this point is included, I'm going to draw a square bracket at 0, 0, and then the graph goes, and it keeps going and going and going, right, to infinity. And so here I can reflect to the x-axis, and I can say the domain is from 0 to infinity. Okay, so that's where we get that one from. Okay, let's look at the range in brown. Notice here my point 0, 0 is included, so my range is going to start at 0. Okay, and since this graph continues and goes on and on and on, it's going to go in a positive direction indefinitely, so it goes to positive infinity. Okay, so notice here we have square brackets at 0 because those points are also included in the graph. And the ends of the graph continue on, so we have those going to infinity. Okay, let's look at the next slide. Okay, next we have the cube root function. We have p of x is equal to the cube root of x. Notice the graph here to the left. This is the graph of a cube root function. And the domain and range are the set of all real numbers. So for both of those, we have negative to positive infinity for the domain. And if we look at it in terms of the x-axis, so this is the left end of the graph. If I reflect it or look at it in terms of the x-axis, it has an arrow, so it goes on indefinitely. So we'll say that that goes from negative infinity. And then the right end of the graph has an arrow, so that goes on indefinitely. So it goes from negative infinity to positive infinity. Okay. For the range, same thing, the set of all real numbers. If I look at the graph, the left end has an arrow, but I'm thinking of it in terms of vertical. So since it has an arrow, it's going to continue on. And so this will go or move toward a negative infinity. And then the top of the graph, same thing. It'll move on to positive infinity. So we have the domain is a negative to a positive infinity for the cube root function. Okay, let's look at the next graph. Okay. Next we have the absolute value function where we have p of x is equal to the absolute value of x. Notice here the domain of this function is the set of all real numbers. So if I look at this graph in terms of the x-axis, here I have the left end of the graph continues on. So we'll say from negative infinity in the right end to positive infinity. Okay, so the set of all real numbers, same thing. And then if I think of the graph in terms of the y-axis, the bottom of the graph to the top of the graph, here I'm starting at the point 0, 0, and then increasing without bound. Okay, so let's look at this. So we're starting at 0, 0. Notice either the left side or the right side, it doesn't matter. We have arrows at the end, so we can see here that it moves in a positive y direction, going to a positive infinity, starting from 0. Okay, so notice here we have a square bracket at 0 because the point 0, 0 is included, and it increases here, so we have to infinity. Okay. Okay, so for the next slide, we have the vertical shift. So we'll start with our first part of transformations. And it says here the graph of y equals f of x plus k can be obtained from the graph of y equals f of x by vertically translating or shifting the graph of the latter upward k units if k is positive, and downward k units, and downward absolute value of k units if k is negative. Okay, so notice here below we have the graph of y equal to the absolute value of x plus 4, and absolute value of x minus 5. I'm going to rename these. So let's call this first graph f of x. Okay. The next graph, we'll call it g of x. So g of x will be the absolute value of x plus 4. And then the last one we'll call h of x, which is the absolute value of x minus 5. Okay, so g of x is equal to the absolute value of x plus 4. If we look at that in terms of the original function, f of x equals the absolute value of x, since I'm adding 4, then that's going to be a shift of the absolute value of x function, a shift up 4 units. Okay, for h of x, since I have the absolute value of x minus 5, this minus 5 operation implies that we're going to have a shift of 5, or a shift down 5 units. So let me reword that. Okay. Okay, and if I think of it in terms of ordered pair, for g of x, since f of x is the absolute value of x, and that's just equal to y, I'll have the same x as my ordered pair from f of x, but my y will shift up 4 units, so I'll have y plus 4. Okay, so that's how I'll get all of my ordered pair if I'm looking at it in terms of the coordinate points instead of the graph. Okay, for h of x, I'll have the same x. Okay, but since I'm taking the absolute value of x, which is my y, and subtracting 5, then I'll have my y minus 5. So I'll subtract 5 from all of my ordered pair of my original x, y coordinates for f of x. Okay, so let's look at the graph. Okay, so let's put f of x, where can we put this? We'll just choose 3 points to kind of see how the graph works. Okay, so here we have f of x, which is the absolute value of x, and for that, this is the function in black. Okay, I'm going to choose 3 points. So we have -1, -2, -3, -4, and then up 1, 2, 3, 4. So we'll choose the point 4, 4, 0, 0, and then positive 4, 4. 1, 2, 3, 4. Okay, so 4, 4. Okay, so we have g of x, which was the absolute value of x plus 4. So let's call this one g of x. Okay. And then we have h of x, which was the absolute value of x minus 5. Okay, and we'll leave that since it's already in blue. So let's put h of x equals the absolute value of x minus 5. Okay, so if I look at this in terms of the ordered pair, let's write the ordered pair down for f of x first. Okay, f of x is the absolute value of x. I chose the ordered pair -4, 4, 0, 0, and +4, 4. Okay, for g of x, we have the absolute value of x plus 4. So here, let's write this. Oh, sorry, it's g of x. Okay, so the absolute value of x plus 4. Notice here we're adding 4 to the absolute value of x, which is initially the y. And so we'll only be changing the y coordinates in order to graph the shift of g of x. Okay, so we'll still have the x coordinates. I'm going to go ahead and write those in. Okay, but the y coordinates will be shifted up 4 units or increased by 4 units. Okay, so if I add 4 to 4, I'll have 8 here. 0 plus 4, 4 here, and 4 plus 4, 8 here. And so our graph of g of x will have the ordered pair of the coordinate points -4, 8, 0, 4, and 4, 8. Okay, and if we check those here, let's check this one first. -4, 8, so I have -4 and then up to 8. This point checks. 0, 4, we'll check this. So we have 0, up 4, that checks, and then 4, 8. So to the right 4 from the origin, and then here up 8, so that checks. Okay, so for h of x, let's go ahead and write this below. We have the absolute value of x minus 5. So in this case here, all of my x coordinates will stay the same. Let's go ahead and write those in. Okay. But since I'm subtracting 5 from the absolute value of x or my y, I have 4 minus 5, which is -1, 0 minus 5, which is -5, and then 4 minus 5, which is -1. Okay, and we'll check those points there. Okay, so here we have negative, starting at the origin, we're going to go left 4, -1. So this point checks. 0, -5, go to the origin and down 5, that checks. And then 4, -1, starting at the origin, right to 4, and then down 1, and so that checks. Okay, so that's how you'd graph it without just shifting the graph. You needed to know the coordinate points in order to graph it. Okay, let's look at the next slide. Okay, next we have horizontal shifts. I have stars beside this because the horizontal shifts will actually do opposite of what you think. Let's read here first. It says the graph of y equals to f of x plus h can be obtained from the graph y equals f of x by horizontally translating or shifting the graph of the latter h units to the left if h is positive, and absolute value of h units to the right if h is negative. So notice here we have the first graph, y equals the absolute value of x. We renamed it to f of x equals the absolute value of x in our ordered pair xy. For y equal the absolute value of x plus 4, we call this one g of x. And for y equals the absolute value of x minus 5, we call this h of x. Okay, so the operation plus 4 implies that we're going to shift the graph of the original function left 4 units. And the absolute value of x minus 5 implies or tells us that we're going to shift the absolute value of x right 5 units. So these do opposite of what you think. Plus 4 means left 4. Minus 5 means right 5. Okay, and so if we think of it in terms of ordered pair, here, if I have plus 4 added within the function or within the absolute value portion to my x, it's going to do opposite of what I think. It's actually going to subtract 4 units from my original x. Okay? For the absolute value of x minus 5, that's going to do the opposite of what I think. It's actually going to add 5 units to my x-coordinate of my original function. Okay? So that's how you determine the graph. If you're not actually shifting the graph manually, you just want to look at the ordered pair. Okay, let's look at the next slide. Okay, so notice here we have the graph of y equals the absolute value of x in black. And then we have our transformations. Here I'm going to call the first one, this will be g of x. And this will be h of x. Okay, so notice here I can just choose one ordered pair. We'll just choose one for now. Negative 4, 4. Oh, and this shows negative 5, but let me correct that. 1, 2, 3, 4, 5. Okay, so I have negative 4, 4. Okay, and notice I have a plus 4. But what I'm going to do is x minus 4 and keep my y. And so if I have negative 4, 4, for g of x, I'll actually have negative 4 minus 4, and then my y will stay the same. So that will become negative 8, 4. Okay, and so notice that the graph plus 4 did shift left 1, 2, 3, 4 units, and also the point 4, negative 4, 4 shifted left 4 units as well. Okay, and this gives us our point negative 8, 4. Okay, for h of x, this was the absolute value of x minus 5. Notice here that this graph did shift from the original graph, the absolute value of x, to the right 1, 2, 3, 4, 5 units. Okay, so for horizontal shifts, remember those will work opposite of what you think. If you're adding within the function to the x, you're going to shift left. If you're subtracting within the function, you're going to shift right. Okay, let's look at the next. Okay, here we have reflection, stretches, and shrinks. So for the first one, it says the graph of y equal to a capital A of f of x can be obtained from the graph of y equals f of x by multiplying each ordinate value of the latter by a. Okay, so notice here y equals a times f of x. That's actually being done to the y coordinate. And so in this case, if you have ordered pair, you're just going to multiply all the y values or the y coordinates by the value of a. Okay. But what that will do is it'll either stretch the graph vertically or shrink the graph vertically. Okay, so it stretches vertically if a is greater than 1, excuse me, and then it's going to shrink the graph vertically if a is between 0 and 1. Okay, so for example, say a may be equal to 1/2 or a may be equal to 0.25. Okay, so if I'm multiplying by 1/2 or 0.25 or 25 hundredths to the function, it'll actually compress or shrink vertically. And then if I multiply, say a is equal to 2, then the graph will stretch vertically. Okay. Okay, for the next one, it says if a is equal to a negative 1, the result is a reflection in the x-axis. So if you think of it in terms of y equal a times f of x, say in this case here it just becomes the opposite. We'll think of it in terms of the axes. If all of my y values become the opposite, and I'll just call this 1, 1, the opposite of 1 would be -1. And so here, this point would shift in this direction. And so my graph would reflect the x-axis. Okay? And so we have examples here. Okay? The graph y equals the absolute value of x, which is our original function. We'll call this f of x. Okay, let's call this next one g of x. 2 times the absolute value of x. H of x equal to 0.5 times the absolute value of x. And then I'll just call the next one k of x, which is a -2 times the absolute value of x. Okay? So, if I have my original function is the absolute value of x, and I multiply 2 times the absolute value of x, then all of my y coordinates of my original function will increase, will not increase, will be multiplied, will be doubled. Okay? And so this graph should stretch vertically. Okay? For h of x equals to 0.5 times the absolute value of x, this graph represents an A between 0 and 1, so it should compress or shrink vertically. Okay? And then for the last one, it's basically a transformation of G. And so as it stretches vertically, it also reflects the x-axis. Okay? So let's look at the graphs in the next slide. So G is 2x, H is 0.5. So we have g of x here. H of x here. And then k of x is not given here. But let's write k of x equal to a -2 times the absolute value of x. Okay? So if we just choose one ordered pair from the graph here, we have -4, 1, 2, 3, 4, 4. Okay. Okay, so I'm going to go ahead and write -4, 4 there also. Okay, and if I look at it in terms of g of x, which is equal to 2 times the absolute value of x, if I take this same ordered pair, -4, 4 from my original, if I'm multiplying 2 times the absolute value of x, which represents my y, because the original was y equals the absolute value of x, I'm going to take my y coordinate and multiply it by 2. So I have -4, and then 4 times 2 would be 8. And so notice here I have, let's go ahead and sketch this. I have -4, 8. 1, 2, 3. So this will be the -4, 8. And so it does have a vertical stretch. Okay. If I look at h of x, which is a 0.5 times the absolute value of x, this should have a vertical shrink or compression. So if we look at that point, if I have a -4, 4, I'm going to multiply, I'll keep my -4, but I'll multiply my +4 by 0.5, or take half of 4, which will be 2. And so notice here, that is a compression, okay, or a shrink. So you can kind of think of it in terms of a Laffy Taffy, okay? If you have a Laffy Taffy and you multiply a constant to that function, it's going to stretch vertically if the value is greater than 1. It's going to compress or shrink vertically if the constant being multiplied is between 0 and 1. Okay? And then for the last one here, which is k of x, that was equal to a -2 times the absolute value of x, which is basically another transformation of g of x. So here we'll have all the coordinate points of g of x, but since we're multiplying by a -2, it will also reflect the graph about the x-axis. So if I look at this point here, I have -4. I multiply 4 by -2, I get -8. Well, in this case here, I plot the point -4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and if I were to choose another point from the graph here, which will be for a positive 8, that graph would be 1, 2, 3, 4, negative 8. Okay, and so you can see here that the graph is also shifted about the x-axis. Okay, let's look at the next slide. Okay, so they actually had to shift there. Okay, so now we have the summary of graph transformations. Notice here for the first one, we have a vertical translation. Remember, this is going to be y equals f of x plus k. If k is positive or greater than 0, the graph will shift up k units. So here, if k is positive, it'll shift up. Okay. If k is negative or less than 0, the graph will shift down k units. Okay. For the horizontal translation, we have y equals f of x plus h, where the h is added within the function to the x. So in this case here, when the graph or when the function has an h that's positive, the graph will actually shift left. A h that's negative or subtracted, the graph will shift right. Okay, so remember, this one is the one that kind of does opposite of what you think. When it's being done to the x, the horizontal shifts will work opposite of what you think. Okay, we have reflection if we have y equal to the opposite of f of x. So keep in mind, if I'm taking the opposite of all my y's, any graph that I have, the opposite of all my y values will reflect the x-axis. And so the graph will have a reflection there. Okay, so let's put here about the x-axis. Okay, a vertical stretch and shrink. Notice here, if we're multiplying a to f of x, if the graph, or if a is greater than 1, the graph will stretch vertically. If we have an a value that's between 0 and 1, it will shrink vertically or compress. Okay, let's look at the next slide. Okay, next we have piecewise defined functions. And the first thing we have here says, earlier we noted that the absolute value of a real number x can be defined as the absolute value of x equal to the first function, a negative x when x is less than 0, and equal to a positive x when x is greater than 0. Okay, so here I would like to also include where it says the absolute value of x equals x. I would like to also include greater than or equal to. Okay, so we'll actually have a defined function when x is 0 as opposed to not having it defined at all. Okay, next we have the definition of a piecewise function. And it just says here that notice that this function is defined by different rules for different parts of its domain. Functions whose definitions involve more than one rule are called piecewise defined functions. Graphing one of these functions involves graphing each rule over the appropriate portion of the domain. Okay, so if we look at this one here, I'm going to split this up as two different functions. I have here that the absolute value of x is equal to a negative x. So we can say the absolute value of x, and I'm going to go ahead and call this f of x, is equal to a negative x if x is less than 0. And then this function f of x, which is the absolute value of x, is equal to a positive x if x is greater than or equal to 0. So notice we have the function defined by two different functions over specified domains. It's considered to be a negative x when x is less than 0. So here, if x is less than 0, that's going to be a negative value. And if I plug in a negative value to a negative of x, I'll end up with a positive. So that covers the left side of the absolute value here. So any value negative will actually be a positive y. Any negative x, if I plug in a negative x, I actually get a positive y. Okay, and then for f of x equal to x, the positive x, when x is greater than 0 or equal to 0, that will cover here the origin 0.00, and all values for x will also be the same values for y, so that'll cover the right side of the inequality. Okay, so let's look at the next slide. Okay, so it says to graph the piecewise function given here. Notice f of x is defined by two different functions. It's equal to 2 minus 2x, and this is only when x is less than 2, and it's equal to x minus 2 when x is greater than or equal to 2. So one way you can think of it is if I have a piecewise function and it's defined by two different functions here, I can say for the first part, f of x is equal to 2 minus 2x, and then also f of x is equal to x minus 2. But it's only equal to 2 minus 2x if x is less than 2. So for any values less than 2, my function is defined by 2 minus 2x. Okay? And then for the second part, it's going to be x minus 2, but this is only if x is greater than or equal to 2. So any values 2 or greater will be defined by x minus 2. Okay, so that's a piecewise function. It's defined by two or more functions over a specified domain. Okay, so if I wanted to graph these are both linear equations. I'll do a rough sketch here and then we'll look at the graphs on the next slide. But for the first one, I have f of x basically equals mx plus b, right? And so we have a negative 2x plus 2 if I change the order. So I put the negative 2x first and the positive 2 next. Okay? And then I have a slope of 1. So here I have a y-intercept of 2. I'll plot that point. And then my slope is a negative 2 over 1. So my rise is a negative 2, meaning I'll drop down 2, and my run is a positive 1, and I'll go to the right 1. Okay? So this line, 2 minus 2x, here, I'll go ahead and draw a rough sketch of it. That's the whole line. But the line is only defined over a specified domain, which is where x is less than 2. So where x is less than 2, here I'll plug in 2. When x is less than 2, then it's defined by this function. Okay, so we'll go ahead and erase a portion of it. If it's less than 2, then it's not going to be defined there. Okay, and since it's strictly less than 2, we can go ahead and say it's not defined there. So it's only values less than 2. And that'll be the first part of the function. Okay, for the next part, we have f of x is equal to x minus 2. Okay, so for x minus 2, I have my y equals mx plus b. I have a y-intercept of negative 2. So we'll plot that point. And then we have a slope of 1 over 1. So I'll rise 1, run 1. And if you want to rise 1, run 1. And if you'd like, you can go the opposite for both. So rise a negative 1, so down 1, left 1. Just so we get an idea of the graph. Okay, so this graph is only defined over the domain x greater than or equal to 2. So since it's only greater than or equal to 2, I'll have to go to 2 and draw a closed dot because it's equal and it's greater than 2. Whoops. And so it'll be everything to the right. Okay, so now we can erase the other part. Okay, so I'm having trouble erasing it, but let's just look at the graph on the other side. So basically, this graph is only defined by the fuchsia color pink and the blue. Okay, so f of x is the combination of these two functions over the specified domain. Okay, so if you notice here, we have the same graph here. And notice that it says that the point 2, 0 is not included, but the point 2, negative 2 is. And that's because here, for the first one, it says x is strictly less than 2, so the point 2, 0 is not included. It's like an open dot or parentheses. And then for the other part here, it says the point 2, negative 2 is included because here we have a domain that says x is greater than or equal to 2. Okay, so that's everything for section 2.2. Make sure you finish up your homework for this section.